5.5, we're going to finish chapter 5 now. All the new stuff that we're going to learn. We're going to be able to take a binomial distribution and do all of these calculations that we've been doing, these normal calculations, right, where we use a z-table, find the probability. We're going to be able to apply that to a binomial distribution. Remember, back last semester, we dealt with binomial distributions. Remember, we did the binomial PDF and the binomial CDF. So we would find, say, if someone was shooting free throws, right, and they normally had a 70% make rate, we would be able to find the probability that they make 3 shots in a row and things like that. That's what we would use a binomial probability for, right? We would say, remember, we would check bins. Was it a success or a failure, right? We have the CDF, PDF kind of thing. So we're going to be able to actually apply normal calculations to binomial distributions today. So we're going to do this stuff. All right, so remember that P was the probability of an event occurring, right? So in that free throw example that I just said, right, P would be 0.70, right? If you had a 70% rate of making free throws, then P in that case would be 70. Q, remember from back in the day, Q is equal to 1 minus P, okay? There is no K, just OK. It's definitely important to know that N times P is greater than 5, and Q is greater than 5. It's interesting. In AP we use 10. So. All right, so we're able to approximate a binomial distribution as a normal distribution when our sample size, n, is large enough. You can see that as your sample size gets bigger, it looks a lot more like a normal curve. And that is what this graphic is telling us. All right, so let's go ahead and do this. 5% of adults. So we're going to see if we can use a normal distribution to approximate our random variable x, and which is the number of people who will reply yes. And then we'll find the mean standard deviation. And if we can't do it, then we'll talk about why. So, yes. All right, so first of all, if we want to decide if we can use the normal distribution, then it's got to be true that n times p is greater than... Are they using greater than or equal to 5? Yeah. I just want to make sure that I'm doing this the way your textbook does it and not the way that. All right. Okay. So what is n in this case? N is equal to 125. What is p? It says 5%, right? So then p is 0.05. So is it the case that 125 times 6.05 is greater than or equal to 5. Wow. Now we can get out our handy dandy calculator and find out for ourselves. So we get 6.25. So that checks out. Is it true that 125 times 1 minus 0.05, is that greater than or equal to 5? Like, for sure, right? Talking about 95%. Oh, sorry, I don't know why I wrote 9 there. It should be 5. That is for sure true, okay? No, really, 95% of 125 is a big old number. So, indeed, we can use a normal approximation. So, it says if you can, find the mean and the standard deviation. All right, so we have a formula that tells us that the mean is n times p. So the mean, mu, is n times p, which in this case is going to be 125 times 0.05, which turns out to be what we calculated before, 6.25. Standard deviation so then our standard deviation is going to be the square root of n times p times q, which is 125 times 0.05. .05 times, sorry, let's kind of that. 0.95, right? 1 minus p. So, taking it slowly, we'll call it the square root of 125 times 0.05 times 0.95. Square root of all of that turns out to be 2.437 if you put that in. So we did it. We calculated the, we found out whether we could use a normal approximation. We found the mean. And we found the standard deviation. Oh. Alright, well, I guess the answer was there. Okay. It's actually, this is a very simple operation for something that sounds weird. We're just going to wind up adding 0.5 to the end of a range, okay? If we're going to find the probability between two values, we're going to find that. Just add 0.5. That's all this is. That's all we're going to wind up. All right. And the reason is that a binomial distribution is not continuous, right? So the little chunky histogram represents what a binomial distribution looks like, right? But this nice smooth curve, of course, is our normal distribution. So we're going to have to just make a little correction so that we may use a normal distribution to represent binomial situation, binomial setting. Alright, so all this is saying is what I was saying, right? We're going to add 0.5 to the left right of a midpoint. Just so that we can get all of it. Alright. Here we go. Let's try it ourselves. We got 38% of these people. I'm going to actually calculate this, just making sure. Alright. They snoop in other people's medicine cabinets. Wow, that's messed up. You randomly select 200 people in the U.S. and ask each if he or she snoops in other people's medicine cabinets. We're going to convert each of these to a normal distribution. Okay. So all you gotta do is make an interval where you do, so this interval is going to be 57 minus 0.05. X is going to be in between these two values, and 83 plus 0.05. So then that interval is actually going to be my bad, not 0.05. My bad. 0.5. So this is going to become 56.5, and this one will become 83.5. It is that simple. That's it. So for this one, at most 54 successes, so X is then less than or equal to, right, at most, or just less than, right, at most 54 successes. So we'll just add, so this will be 54 plus 0.5, and this will become just, all you gotta do is just add 0.5, or subtract 0.5 from each end of your interval. Alright. So here we go. We're going to use a normal distribution to approximate binomial probabilities. First thing we got to do is see that we have an N, P, and Q, right? Does the binomial distribution apply? We can check bins, right? We can check for if the situation is either a success or a failure. Is each trial independent? Is there a set number of trials? And here's the probability of success. This trials, checking bins. Then find out if we can use a normal distribution. We'll find the mean and the standard deviation, and then we'll be able to use essentially a z-table, right? The normal distribution, right? We'll be able to use a standardized value in order to calculate some sort of a probability. So that's what we're going to do. And that's what I say, right? We'll apply an appropriate continuity correction. So let's just do this. There we go. All right. Let's to a big old problem. 5% of adults in the United States are planning to purchase. Oh, same one. All right. I'm going 3D TVs, 5%. Okay, so I see this 5%. If you see a percent in this problem, immediately you got to think to yourself, that must be P. It usually will be. All right. You're going to randomly select 125 adults. So if I randomly select 125, that's telling me that N is 125. Ask them if they're planning. What is the probability that more than 9 respond yes? So what we're looking for is the probability that X is greater than, and now we're not going to use 9, we've got to use that continuity correction. So we're going to add 0.5. Almost. We won't add a whole point, but we'll go 9.5. So that's what we're looking for. Huh? Yeah, on average, yeah, but what it's doing is just making it so that that our normal distribution is a little wiser. It gives us a higher margin of error. Yeah, you're right. It doesn't make sense for 9.5 people to say yes, but mathematically it helps us find a more accurate problem.
So that whole thing where you're seeing if it's greater than equal to 5, you can solve it or not?
Yeah, so we're gonna try to use a normal distribution for this. We haven't determined if we can yet, right? So we're gonna find a z-score, or we could use normal CDF in our calculators, as long as our conditions are met. So Q then is 1 minus 0.05, so it's 0.095. 0.95. Alright. So let's check our conditions. Let's check if N times P is greater than or equal to 5. And we need to check that N times Q is greater than or equal to 5. So we got to check these things. Alright. We already did that, right? We already said that 125 times 0.05 was indeed greater, and we found out that it was 6.25, right? 6.215. Um, 6.25. So that checks out. And then it's also the case that 125 times 0.95 is greater than or equal to 5. We'll go ahead and calculate just to be thorough. So 118.75. That checks out. Because those two check out, we are allowed to use a normal approximation for this, right? So we can find a z-score and use the table, or we can just go ahead and go to our handy dandy calculator, put in normal CDF. I'm going to run out of room there, sorry about that. Normal CDF with our lower bound has 9.5, right? Looking for a probability that it's above 9.5, so my lower bound is 9.5. That means my upper bound is what we're representing as infinity there, a big old number. And then our mean we're going to use, we still need to calculate that. We agree? No. So we need a mean. Huh? Yep, our mean is 6.25, we calculated that. And what did we say our standard deviation was from previous? I have it here, hold on. 2.437, thank you. So then mean 6.25, standard deviation 2.43. All right, let's put that into our calculators. All right, so we got our calculator, and we will go to menu, probability, distributions. Same place we've been going the whole time. Normal CDF, our lower bound was 9.5. Upper bound was 10 to the 99th power. Mean 6.25. Standard deviation 2.436. We get a probability of approximately 0.091. So this is equal to 0.09. So the probability that more than 9 respond yes is 0.091. Oh my gosh, we get to do it again. Yes. All right, let's go ahead and find this probability. 58% of adults say they never wear a helmet when riding a bicycle. Bad idea. So what does that mean? That means that P is 0.58. And then what's Q? It's going to be 1 minus 0.58 or 0.42. All right. Fantastic. Also, we know that N is 200 because we've randomly selected 200 adults. And we're going to ask them if they wear a helmet when riding a bicycle. So, first thing we need to do is decide, hey, can I use a normal distribution to calculate this probability? So, N 200 times P, which is 0.58, is that greater than or equal to 5? Yeah, it is. It's going to check it out. And then is N, or 200, times 0.42 greater than or equal to 5? Heck yeah, 42% of 200 is definitely bigger than 5. So we can just check that off. Once we've done that, let's go ahead and calculate our mean, which is N times P, which is going to be 200 times 0.58, which is 116. And now we'll calculate our standard deviation, which remember was the square root of N times P times Q. So in this case, that is 200 times 0.58 times 0.42. What is that going to give us? Times 0.48 times 42. So we're going to get about 6.35. Okay? What's the probability that we're looking for? We're looking for the probability that x is at most, so less than 100. Well, remember we have to do that binomial correction, so it's going to be less than 100.5. We're going to add that 0.5 out at the end of whatever we're doing. Okay. Fantastic. Now we can go straight to our calculator, and we can get, we can do normal. I think we're run out of room there, so we'll calculate normal. CDF. Our lower bound now is negative 10 to the 99th, right? Because it's everything less than. Our upper bound is 100.5. Mean is 116. Standard deviation 6.35. Let's put that into our calculators. All right, menu, probability, distributions, normal CDF. That lower bound will work, right? The upper bound we said, whoa, this is really weird, was 100.5. The mean was 116. Standard deviation was, I don't remember, 6.35. 6.35. Calculator probability. 0.007. That is very, very low. All right. .007. So really low probability. So the 0.7% chance that if you were to randomly select 200 people, that you would find that 100 or that less than 100 are wearing that. Should have more people like that right now. You need it all. Ready? There. All right, so we'll pick up with this one next time. I think that we are about. Yeah. So there is the summary. This is your homework for the lesson.